Good afternoon. Welcome back. It's my great pleasure to introduce this afternoon our first keynote speaker, Drago Anguelov. Drago graduated with a PhD from Stanford University in 2005. His advisor was Professor Daphne Koller, and he also collaborated a lot with Professor Sebastian Thrun, known for his pioneering work in self-driving cars. For his PhD, Drago focused on applying statistical methods to computer graphics and robotics. And after 2 years at Like.com, he joined Google in 2007, where he spent 8 years, first working on 3D vision and pose estimation for Street View, and then later doing research on computer vision for annotating Google Photos. And his team is also known for pioneering some very popular architectures like the Inception network. And since 2018, Drago joined Waymo to lead the research team, which focuses on developing state-of-the-art machine learning algorithms for autonomous driving. And today, Drago will describe recent Waymo machine learning research that addresses the complexity of the world of driving environments.
Thank you for the kind introduction, and thank you guys for having me. So today I will tell you a bit more about our domain and about the problems in research we have been using to harness and enable better driving. Waymo is Alphabet's autonomous driving technology company. We're building a driver, and our mission is to be the world's most trusted driver. And that's a tall bar, and we take it seriously. Trust needs to be constantly earned, both through thoughtful design and testing, and of course, engaging the communities where we drive. And we're already out there, and one can say that there's already some impact from and benefits from our technology. 22 million miles. There's an analysis on our safety hub on the website. Is relatively a small number of miles compared to everything people drive. But even there, when we analyze our fully driverless operation and compare to our estimates, the statistics of people driving in the same locations as we had, we see significant improvements in various safety critical buckets. Maybe the left one is the most safety critical type of accidents, and we are there improving almost 6 times. And then you have on the right a bit less severe buckets. Say fewer reported police crashes, we're improving about a couple of times. And so, of course, we continue driving. It's still early, but it's a promising start. And we continue driving today in fully driverless mode in 4 cities, of which San Francisco and Phoenix are the biggest and most markets and most mature at this time, where one can just download the app from the various web stores and just order a Waymo car. With Los Angeles, we started scaling recently, and there we're still working through our wait list. And Austin, just last week, I believe, we invited some first batch of external folks to start riding in our vehicles. This is still relatively early, but we will continue expanding there. At this time, we're serving over 100,000 rides a week to customers. And this number is quickly increasing. Actually, I think the time it took us to go from 50,000 to 100,000 was about 3 to 4 months. So that's the latest reported kind of interval we had. And so we continue thoughtfully expanding. But I think the other exciting news is that we are working on our next generation vehicle, which is focused on significantly simplifying the sensors, the compute, making it more affordable, but also delivering a good rider experience. It is designed explicitly to be a taxi vehicle with a lot of ease, for example, here of getting in and out, fully automatic doors, which are always great for autonomous vehicle, and so on, right? And so hopefully we can deploy that in the not so far future, where you guys can experience this new hardware. But this talk is primarily about software and machine learning. And I'm not sure how many of you have worked on autonomous driving, but I will give a few primers and then describe to you some of our work that helps improve and enable the kind of driving you can experience in our cars. And what is autonomous driving problem? Ultimately, you have a vehicle equipped with sensors, in our case, camera, LiDAR, radar, a few of them in various positions on the vehicle. And you want to drive, so you want to actuate the steering and acceleration of the vehicle. And that's what the driving agent is supposed to do. And on a high level, this is, of course, great, but it's a very difficult problem. Maybe the output looks simple, but the input and the situation is quite complicated. And it makes it different from some of the other applications of AI or machine learning models people may be looking at, right? So what are aspects of our domain? One is it's a complex physical environment. So the set of possible inputs that we need to handle is very large. It spans different areas, types of area, weather conditions, times of day. We have many sensors, over a dozen camera, half a dozen LiDAR and radar, collecting hundreds of millions and more readings per second. And you need to collect and reason over data over multiple seconds to properly understand a situation in the environment. There is a lot of complex interaction with humans who don't always follow rules that one needs to mitigate and address as we traverse these environments. There are high performance requirements. It's safety relevant domain. You guys understand that can be serious outcomes from suboptimal driving. And there is a very long tail of scenarios of rare things that can happen on the road, which is challenging. And last but not least, right, we need to do this on the vehicle in real time. A lot of the situations require quick reaction, and there's also, of course, limited compute on these vehicles. So we have all of these aspects that make our problem quite unique. And we have a product addressing these requirements, and perhaps it is the most mature manifestation of embodied AI. I may be biased, but it's in the running there. And I think it's one of the early cases of a robot being out there interacting with entire cities. And so I will show you the kind of reasoning and the kind of situations we get to encounter to give you a better direct feel for our problem. For example, there are situations such as construction and instruction by policemen or other people. Here's another example of construction, but then we need to also navigate additional traffic that is trying to potentially squeeze in around us. Here's a case of a blocked lane where they blocked it. Here's an interesting case. If you see, there's a vehicle behind us and a truck coming at us, so we need to navigate both between the car that was behind us and the truck and understand that we should actually back up. You can see this is all these examples are from fully autonomous operation of our vehicles. Here is a case where you can see that we don't always get to just drive in our lane and make progress in a simple way. There is complicated agents and crowds. One needs to ultimately be able to navigate safely around. So it's not that structured as one may think. Right? And there can be many, many agents you can see above our understanding. This is bad weather. There's rain. There's actually a traffic light that's turned off there. But we stop cautiously at the intersection, and some people just blow it. And this is another case. There's a truck coming at us, and you actually need to understand and go all the way on the shoulder to avoid it. Otherwise, there would be a collision. So there's all kinds of cases like this, which do show you that how varied and potentially difficult driving can be. And there is the long tail as well. So there are things we have actually directly observed. Well, people biking and toddlers on the loose. That's terrible, but happens. Falling skateboarders from trucks right in front of us. There is grills falling from from, I think, pickup trucks on the highway, trees fall, floods, right? And you get the idea. I think as we drive today, probably at least a person's lifetime of driving every week or more, we keep encountering more and more difficult cases. And so AI in machine learning has a big role in enabling our product, because it's a great way and a general tool to address a variety of difficult cases that can arise. And of course, the promise is we have this rich sensor data, and we should be learning how to understand and predict the environment that we observe through our sensors. And another thing that's really great for us is that we want to learn from human driver demonstrations. We observe how everyone else drives in our environment. So that's a ton of examples of behavior of drivers. And that's a really rich data that a lot of other robotics domains do not have, but it's an advantage for us. And I think ultimately the challenge is generalization. How do we learn the most from the data we observe? And I think that this underpins a lot of our research. And today I will tell you about several aspects of work that we've done. And there's a lot more, of course, that I won't get a chance to present that help you advance the possibility, how much do we learn from the data we collect. Now, because not all of you are autonomous vehicle people, just a high-level observation of the stack. There's a set of sensors. There's a perception block that takes the sensors and aggregates this information, represents the environment in some way that is suitable then for us to predict what others may do and plan our actions in that environment safely. And then these plans are passed to the controller, which executes a set of controls and drives the car. And again, maybe this is a challenge, but there's a lot of sensors on these vehicles. And so all this data needs to be processed in real time, right, from at least a dozen cameras or so, if not more, and LiDARs and radars in our case. And then, right, we build a representation. And what's worked traditionally in autonomous vehicles is you want to fuse all this information from all these sensors. And this bird's eye view, which is Euclidean space centered around the autonomous vehicle, has been very popular. So if you take all this information and you fuse it into that coherent single frame of reference, that is furthermore not just perspective projection, but allows you to reason directly about 3D geometry. It's shown traditionally that it provides benefits in generalization and so on. So it's adopted in many of the modern stacks today. And there is also an option, and every company designs it a little bit different. You can have intermediate explicit outputs in this space, or generally from the perception stack, such as 3D objects boxes for the objects in the scene with attributes that you may reason about. There can be occupancy grids as well about more stuff type or more uncertain types of quantities that boxes are not as suitable for, and you can have many, many more of these. There's map and other kinds of objects that as well one can explicitly extract. And so all of this representation then is passed to downstream where you plan your actions. And so these intermediate outputs, that's a lot of the work happens there. Think, what is this representation of the world? What should be in it? How do we build it? This is constantly evolving. And these intermediate outputs have a set of pros and cons. So we found that improves generalization if you have also all these labels and things that are natural for people. If you ingest this knowledge into the model, it's likely to generalize better. If you have these intermediate outputs next to your plans, you may be able to validate if your plans are consistent and reasonable relative to understanding the environment. You still may need some of these outputs to build a simulator to understand, okay, here's where all these objects now in the simulator, maybe I populate them with all these agents. If you do not have any explicit representations, you need to solve the simulation problem in some other way. And generally, there is this notion that perception stack is also a compressor. So the census is a very high data pipe, a high bandwidth data pipe, and you want to, if possible, compress it in some way. because eventually when you store all this data and when you want to do prediction and planning, you typically need a lot more temporal data for prediction and planning. Events happen rarely that are interesting. There's tons of objects otherwise and sensors you may be collecting. So these are kind of things to think about the world representation. And of course, there's cons. You need to do feature design. If you put this output, someone needs to, well, select them, label them, and so on. And that can add complexity. And then how many of those can you add explicitly? So there's a push and pull here. And I think a lot of engineering sensibility goes into evolving this. But that's roughly the stack. And so now I'll show you just one example of a representation we have used before and researched. This is what we call pedestrian key points. So here we're trying to understand the behavior or what the policemen are telling us with gestures, so we know how to proceed. This is a real example off of Reddit. So you can see us. You can see there we explicitly reconstruct the poses of all these agents, and we understand which ones may be policemen. And then you can see that we're waiting, and it's not our time to go. But eventually, I'm not sure where it's better to look, on the top or on the bottom, but eventually they say, OK, go. And here it is understanding the gesture and going, right? So my talk is about several ingredients for scalable AI driving stack. And of course, when you talk about this, we start with architectures. And this bird's eye view representation maybe is more specific to our domain. And so the question is, what are effective transformer architecture for bird's eye view processing? And we have a paper maybe a couple of years ago pushing in this direction. So the idea with bird's eye view is, OK, so you can represent and transform and fuse the sensor data into this space around the vehicle. But this space can be very big. So you want to see sometimes over 300 meters away from the vehicle. And so now imagine quadratic space, 300 meters on all sides. It can become quite prohibitive. Or if you think of it as pixels by 10 by 10, say, cells, that's quite a lot of cells. So quadratic complexity in this is quite suboptimal. And so we have worked on an approach called sparse window transformer that processes all this space without incurring quadratic cost. And so that's an architecture that improves on previous convolutional methods that we also explored for the space. And also benefits of this one is it's more compatible with TPUs, which we have at Google. But essentially, it's a model derived from those that work on computer vision may know Swin transformer. So Swin transformer splits the image into patches, processes each patch, then moves the patches, the patch grid some distance, and keeps reprocessing over different patch grids to reconstruct features in multiple layers. So here we do a similar story, only you start with the bird's eye view feature map. And this feature map is sparse. And in this example, or in the paper, we do it with LiDAR. But this can be done also from cameras. As long as you can extract information and sparsify it and put it in this bird's eye view grid, it's generic, actually. And so here, the way it works with LiDAR is we process the point cloud. And in each vertical pillar, there is some embedding that is stored wherever there is LiDAR. That's typically how it works. So you have this sparse top-down view set of embeddings. And we start splitting it and processing it with our sparse window transformer blocks, where each takes a 10 by 10 region, given a certain tiling. And we apply self-attention to the region always in a sparse way. And then in each block, you're allowed to shift the regions at most once. And occasionally, we change the scale. So it's a pyramid processing architecture as well. The point is, this, if you read the paper, you will see details. But essentially, we managed to do the whole architecture without ever incurring dense processing in bird's eye view. And as a result, we achieve, at the time, state-of-the-art in quality while being dramatically faster than all similar approaches. Which is quite useful, I think, for the use cases we're talking about. And this is an example of what this does. So this is us driving on a highway. And there is at least 200 meters distance, this is just frame by frame. It's a research paper. We process one frame by one frame the boxes. And this runs faster than real time. And you can see what we can do. So this is no tracking, no memory, no nothing, just LiDAR. And you can get that. And then, of course, you can do the same thing at night. And in LiDAR at night actually works better, if anything, than during the day. And here there was actually an accident, and you can see it quite well in the detector as well, up there in front of us. But that's an example. So that's what I wanted to tell you about transformers for parts of our perception stack. Now let's move to behavior. That's a key part of our domain. Actually, what distinguishes it is multi-agent. Our robot interacts with the humans around, whether they're pedestrians, bicyclists, driving vehicles, and so on. And we need to be able to anticipate and model these behaviors of folks so that we can drive safely. And this is a long-standing area of research and a focus for our domain because it's so core to everything we do. And we've been working on this since I joined Waymo. We always had work on this topic. And this is maybe one of the earliest instantiation of this. It's a model called multipath, which formalizes the problem. You have a set of inputs, a world state, which was the agents, the traffic lights, the road graph. All of this comes into a deep neural network. And then we predict, essentially, for all the agents in the scene, it's like a probabilistic mixture of Gaussians. You have k trajectory modes with probabilities. And for each, you have some spatial uncertainty around the predictions. And this covers potential futures for every agent. People are not deterministic. You need multiple futures. This is a probabilistic model. And this is an example of some visualization of one of the models that we were building. Up to 8 seconds in the future for every agent, pedestrian on the sidewalk or vehicles up there on the road, you can get the predictions of our research model. And then, of course, we took that model and we upgraded it when time came to transformer architectures, significantly streamlining, simplifying. You may recognize some kind of more standard encoder or decoder model, and improving the performance along the way. Now, there is an interesting problem with this general formulation that I described when you predict k trajectories per agent independent of each other. For simplicity, this is marginal a posteriori prediction. But it's somewhat suboptimal, right? So you want to understand, here's 2 agents. We predict their futures. Each of them independently by itself may make sense. So this one guy could go straight, that guy could turn. But together, they don't quite make sense. So actually, you want to model some version of the joint likelihood of probability of behaviors, not marginal a posteriori every agent by themselves, even though that's the simplest and most tractable thing to otherwise do. And we, of course, evolved our models, and we have several versions. But one of the interesting ones is a paper called Motion Language Model. And it drives directly the comparison to language models. And you can think of driving being a conversation between the participants, where they emit motion tokens at each other as opposed to language tokens. And you observe all these motion tokens, and you're trying to predict them, right? So this is a motion token sequence by these guys, and I think I went too far. But essentially, then you can design a model and a decoder that emits these motion tokens for groups of agents in the scene, and then just sample sequences of joint motions with this model. And again, it's the similar architecture, and you can train it with teacher forcing or in other ways. And it can do this at inference time, the usual causal cross attention, and produce different futures. Every sample is one future. You can sample again, you get another future, right? And there's a very simple, relatively speaking, and quite language model convergent architecture. And now you can, of course, do joint behaviors where the marginals, again, do silly things because each is modeled independently. And here, this joint model, of course, understands that if the, well, in this case, I believe it's the bicyclist or pedestrian starts going, the vehicle is likely to wait and not the other way around. And this model, again, on some academic benchmark, compared to some of other model of ours. These are main metrics, most robust, or like they measure the long tail the best of the metrics we have on these challenges. This was state of the art on those metrics at the time. And so I just tried to give you an intuition for at least two of the main types of architectures that are somewhat distinct or relevant for autonomous driving, with research illustrating with our research. Now, of course, the question is, OK, what about model scaling? That's another popular way to improve the quality. And does it work for our architectures? And of course, we studied them. And so for this motional M architecture, I'm going to show you an example of scaling laws, right? So we took it. And these are isoflop curves where we ran models of different sizes. And we collected the performance of these models across as a function of parameters for their different, I think, or a number of examples. In the black, you have the optimal size of model for that amount of compute. And so then you get some kind of scaling laws as a function of compute and or data. I think, yeah, examples in the second curve. And so compared to language, what we found is, so we want to increase, at least for these curves, and we need to keep continuing them. We actually internally have a bit longer set of points on these curves. But we want to, typically for these types of models I described, for modeling behavior, model size increases about 1.5 times as fast as dataset size. And compared to LLMs, for the same compute budget, our models are about 50 times smaller. So that is interesting. We are still trying to understand in more detail why exactly this comes out. But I think one of the intuitions is some of the rare things we do care to model are potentially more rare than in language. So in the sense that you may need to go through more data to observe them. So the model is small, but you need to go through a lot more data to cover the rare cases in our case. There's a lot of common cases and few rare cases. So it's example hungry to get to them. But that's just a hypothesis. We don't fully understand. But the good news is the scaling laws work. And we can scale models and get better quality and potentially distill and retain some of this quality. These are some more maybe endpoint metrics. This AD metric is a notion of did you predict a trajectory close enough out of a budget of trajectories you have guesses compared to what those agents actually did. So lower is better. And this is a power law. And the prediction is quite close to the actual estimate for the last model. So just an unusual example that they seem to so far be predictable and hold. And we've tried other metrics. These are pure prediction metrics, fairly straightforward. But there is the other interesting example, which is you can do also scaling laws as a function of compute. So the compute factors in these models because I can keep sampling more and more futures. So instead of drawing 6 samples and seeing what the statistics come out, I can draw 1,000, and then I can cluster them. And then I have a lot more statistically significant set of modes. And so you can turn compute into quality. And this is an example of this. So there's models of 3 different sizes. And you can see that if you don't have much compute, eventually the smaller model asymptotes, and you benefit from just going to a larger model when you have more compute. But for a while, you can keep gaining quality by running more samples. So this is maybe similar to language, but we also see this kind of lever. And this is an example of what scaling gets you. So this is a model with 1 teraflops compute. And there's a situation where you're entering an intersection and someone's blocking you, but you should understand. And even though you're tilting to the right, there's a case you may actually want to go around them and proceed straight. And this is fairly rare to have you're already leaning right. So this is fairly rare to get that you actually may want to recover and you're there because someone was impeding on your way. And so the smaller models may not necessarily capture that. So an example. Now, another interesting problem in our domain that's quite relevant is we do typically have some other outputs as opposed to just driving, acceleration, and steering. And so for those outputs, perception outputs such as bounding boxes are popular, or other semantic segmentation may be popular. They're good to have. They're useful for reasoning where you're running into things, but they can be expensive to produce, the labels for those, right? Especially in 3D. And so we have been working on ways to auto-label this, and this is, again, maybe started roughly not much after I joined Waymo. But the intuition is like this. So on the vehicle, you only see, you only have the past and the present available to you to understand the scene. But once you've driven the scene, you also have the whole sequence, including the future for any one point in time for that you're trying to essentially perceive. So you can use the whole run sequence, aggregate all the information, and now you're trying to reconstruct what's the ground truth state of the scene. So we call this off-board perception. And this is an example algorithm we published a long time ago where we actually labeled with this algorithm our benchmark, the Waymo open data set, fully auto-labeled. This sees past and future, the whole run of the vehicle through the scene, and reconstructs some fairly accurate shapes and stable across time. And then, so that was great. But we also found a way to improve it. And I will show you another example of this kind of technology that's interesting, and it's relevant for this spatio-temporal robotic domain like ours. So it's a work called MORAR. And the idea is like this. Hey, we have already this behavior prediction capability. If we observe an agent moving, we have pretty good guesses where it might go, at least in relatively short periods of time. So can we use now this type of understanding to improve this off-board perception for agents? Use behavior prediction to essentially move information over longer periods of time. And so this works a bit like this. So you have, say, some point cloud sequence or scene representation in bird's eye view, and you break it into 1 second chunks. And each chunk you process, you apply some detector tracker, and then you also apply a motion prediction model for your object. So now with the motion forecasting model, you can pass where you think this model will be several seconds out in the past or in the present. And with this model, you take this object and its track, and you essentially create points for other points in time, virtual points. So you say let's say you want to cast it 3 seconds in the future. You're going to make a point 3 seconds in the future from the future prediction with this behavior prediction model for the object from 3 seconds in time. So you make these virtual points, and you cast them across time. And when you do it, essentially you augment now for every each one of these 1 second sequences. Now you add these points. Says, hey, I believe that at your time, from some other time, we're casting this knowledge for these other objects from 3 seconds away, right? So they're virtual points. They augment your cloud. And now you apply your models to the joint cloud between both the predicted virtual MODAR points and the original LiDAR points or whatever representation you had. And so that allows you to do better. And this is several different detectors where if you apply the technique, all of them significantly improve their performance and allows you to handle things like occlusion a lot better now that you have this cross-time reasoning as opposed to if you don't. So it's a very flexible and simple model that allows you to flexibly aggregate long periods of time for moving agents. And last but not least, you can do similar tricks for semantic segmentation in 3D. We have cameras, we have LiDAR. We can take it all and build a semantic 3D model of the scene by aggregating the semantics for everyone. So it's a bit like this. So this is automatically reconstructed, both geometry from camera and LiDAR and the semantics. And there is like, I don't know, red signs, yellow traffic lights, lane paint of different kinds, curbs, obstacles, and so on. So we get, and these, of course, can be reconstructed because you're aggregating data from tens of seconds. You can see hundreds of meters away and auto-label it for your current frame if you need to. Useful for many applications. So that's an interesting spatio-temporal capability for our domain that we find helpful to scale certain types of data. And last but not least, oh no, there's two more, but one of them is, well, so far I showed you a bunch of technology, but we're building agents. And these agents make decisions And then these decisions play out over multiple steps in time. And so if you do motion LM, like I showed you, with simple teacher forcing or train it one step at a time, they're susceptible to covariate shift. Covariate shift is the problem where small errors in prediction or plan in action accumulate over time, taking you out of domain for your models, where you make bigger and bigger potentially errors now that you're out of domain, and then you off your learning manifold and your models start behaving badly, right? And so you want to potentially train your models in closed loop, meaning you want to train them to behave well over multiple periods or multiple steps of time, and you want to play whatever policy you've learned for these agents over some amount of steps and train these policies to not get into trouble. Now, the challenge for us, unlike language and other domains people may do, is that language is its own simulator. You write words, and words beget more words, and so on. And in our case, it's a physical environment. There is continuous driving. There are physics. There is even controller lag properties. There is agents in the environment that behave in different ways. So I can give you a whole other talk about what it takes to apply machine learning to build such a simulator from data, which, sorry, today there is no time to do that. But imagine someone built you this simulator, which is a talk like this. Now, assuming you have this simulator, you can train even better agents with it and more stable. And there's these typically two techniques that apply imitation learning, where we're just trying to teach the agents the usual maybe train a discriminator, model-based adversarial imitation learning or other techniques. You're trying to imitate the humans as well as you can and not get out of distribution in the futures. And there is, of course, reinforcement learning methods where you can specify rewards and try to ensure that your agents behave consistent with the rewards in that simulator. And we have a paper where we try to combine both. And we found typically demonstrations are more effective, of course, in the high data regime, and rewards start getting more effective in the lower data regime. And there's many ways to do this. It's a big space, and I think still very popular also for many domains. In our case, we experimented with a very simple algorithm, kind of behavior cloning soft actor critic. And the high-level idea is, hey, when we're in distribution, we use both the imitation and reinforcement learning laws. And otherwise, when you're in policy and get out of distribution, you just use reinforcement learning laws, like don't collide and don't with things, don't get off-road, and so on. And you train. And generally, we see improvements from this technique when you have a reasonable simulator. In these examples on the left, an advanced imitation learning method, MGALE. And in that case, it clips way too close to a person coming out of a vehicle. That's not the best behavior. And when you add reinforcement learning with rewards that encourage not colliding, you get a little bit more conservative, cautious behaviors because you're really trying to avoid these collisions, right? So there's some interesting properties. But in general, this is part of our setup. We have to think a lot about these issues and mitigate them and work around them and potentially train accordingly. And one interesting topic, which a lot of you otherwise talk about today, is large language models and vision language models. And I think they have made tremendous strides, and they have great capabilities. And generally, you've seen many of these things, right? Like, these are not what our models traditionally could do. But you can, that's San Francisco, I believe, right? Can I park now or not, right? And I think this example on the web was cool. Eventually, it tells you I can park for an hour until starting at 4 p.m., which is awesome, right? But it's a good capabilities. And of course, there can be very unusual, rare scenes. And there is a lot of knowledge that can be present in these models, explaining to you the context and roughly what you should be doing, right? That we could benefit from. For example, there's been a serious accident, car has flipped onto its roof, emergency respondents are there, we need to consider an alternate route, or we should avoid hindering the emergency response. Actually, great advice. That's very important for us. We should not start trying to blast through this scene as these people are working. So there's a lot of good knowledge here, right? So we want it. And we've been working with LLM and VLM in our domain for a while and exploring it. So I'll just show you some research we've done maybe 2 years ago. It's a natural thing is to say, OK, so they have all this knowledge. Can I extract it and use it somehow? And can I distill this knowledge into our models? And this is a paper we did maybe 2 years ago and came out in 23, where you can essentially have a method without any labels whatsoever, just with a vision language model. We can run it and align it with our LiDAR models to essentially auto-label and learn to detect a whole bunch of moving objects without any human labels. And it fairly open set way where you can have things like, is anyone jaywalking? Or is this a Jeep? Which is not labels necessarily we would apply in the general setting. So that's one type of work, right? So take vision language models and annotate data and distill it. But the other way, which is interesting, is, OK, so can we also try to apply them for our tasks and study how they behave? And we've done this too. And this is a case where we took a vision language model and we started applying it to some of our autonomous vehicle-specific tasks. And one of the main tasks that is very natural to apply it to is motion prediction for the vehicle. This is very close to planning, but not quite, because it's not like you're acting in closed loop on your predictions. Just at any one point in time, you're asking the model to predict some future waypoints for the next few seconds of what is your driving profile, likely driving profile, right? Or profiles. You can predict several, like our previous models. And you have a route. You have a command, which is, go straight here to this intersection, turn left. You can have some status in language where it tells you where you were, what your speed was, where were you the last few seconds. And then you just have some images from the model. And we can fine-tune it and see how well we do. And so we explored this. And so when we did this, we applied it to several benchmarks. One of them is new scenes. It's popular, but it's actually small and limited, so don't read too much into these results. But main point is when we train this model, it's roughly state of the art. And when we actually train it on our internal data, it's competitive or better than the state of the art, which is good. So it means at least not a bad model, right? But that's a good property. And then once you have that, you can start doing other things. For example, you can do chain of thought. And we can take again, models and auto-label data and data sets with captions and rationales and what we call critical objects. You can analyze in our logs which objects affect our driving based on our current stack and learn to annotate them. So you have all this training data, and then you have the model provide you several types of rationale or descriptions of the scene, and only then you plan your trajectory waypoints. And so it can be things like, hey, there's these two critical objects, and here's what the first one is doing, and here's what the second one is doing, and I should generally try to keep speed given these objects, right? And then you predict these waypoints. And of course, what we see is somewhat interesting. Scene description is some high-level description of the scene. There is a scene, your intersection in the city, and there's this many lanes, and so on. So these are the type of descriptions, and we ablate it. Actually, high-level scene descriptions don't seem to help. But identifying critical objects, describing roughly what they do, and then describing your high-level decision of what you plan to do in that case seems to improve the ultimate actually waypoints produced for our future trajectories, which is kind of nice, I think, again, confirms the general technologies apply. And then the next step from this is, OK, well, this is mostly just language-based chain of thought, rationale description. Can we build one model and just train it to do several of our tasks that are very specific to autonomous driving, such as 3D object detection or road graph estimation as a set of points itself, right, similar to the trajectories we drive. And then depending on the prompt you give the model, it gives you a different type of output, right, that corresponds to the task. So it's a generalist type of model. And so we built this model, and then we studied how do these tasks affect each other as well. And actually, first I'll show you what it looks like, which is kind of cool. So take on the left, you can see in yellow is our estimation of the road. based on this picture, and then you can see the 3D boxes of the vehicles. This is our own trajectory, here the points, if you really squint. And then you can see how it predicts that we're driving, and now it sees a dog, and it predicts that we should be stopping. The green thing disappears. And yeah, and you can see generally it does a pretty decent job on these boxes and the road graph. And here's another example. This is Chinatown, I believe. You can see there's people, riding on back tires and so on, but it still detects and tracks them. And you can see generally quite reasonable, at least in 2D as I show it, performance. But it's actually not bad in 3D also. And there's some reasonable road graph estimation as well. So that's what it can do. And we also see that these tasks generally enrich each other. So training with more than one task tends to lift the boat for the others, because they're related. And I think, again, it's a bit different mechanism than chain of thought, and maybe the two needs to be combined. But this is a good property to see that the more we teach it to understand about this driving environment and the relevant tasks, maybe the better we get. Now, that said, so that's great, but there is limitations to VLMs and areas that they should be improved to be able to do some of the things that we're able to do today with our current models. One of them is fuse multiple sensors better and over time. Accurate spatial reasoning, this is still area of work for these models. In 3D, it's helpful to do this in 3D because then you can apply additional safety checks on the things you do. It's a bit hard to do if geometry is lacking in your outputs to apply safety checks. Long-term memory we talked about. Also compute and scaling efficiency, right? These models may require a lot more processing and a lot more training data to get to decent results compared to more custom architectures, right? But this is an area that's interesting. Still, they can do good things, and it's promising. And so at Waymo, we've been working on taking the best of what we've been able to develop with our AV-specific advances and leverage this general world knowledge and capabilities of vision language models to build our next generation stack. And so we refer to this stack that we're working on as the Waymo Foundation model. Right, and I'm not going to have time or the chance to go into a lot more detail with you today, but I show you kind of a high-level diagram of how we think about it. There's these two main modeling components. There's the perception encoders. There's a big box that fuses all these sensors and combines the data from all these sensors and potentially a map over time. And then there is this model for decoder, which also can be prompted with questions and so on. But this model essentially predicts the future of the environment, your future driving, the future behavior of others. It can interpret the state and describe it, right? It can predict not just future states of the agents, but maybe traffic lights and a bunch of other properties that may happen in this environment, right? And so this is on the way. We have made some progress along this vision and direction, and I'm excited about the progress we've made, and I hope that in the future I'll get a chance to share some more of the details there with you. Now, of course, just to finish, this is all great, models are good, but they're in service of this vision of building a service delighting riders. So in the end, it's all in service of this, right? And for those of you that have not experienced this, I hope you do.
Let's get this day going. Let's go. Got our own personal driver, my favorite driver ever. No driver.
This is pretty awesome. Driving us?
So it can delight riders and earn their trust and safely deliver them where they're going. I will also play a video of set of things we've dealt with as we were delivering these rides. They are all incidents where you can see our vehicle reacting to stuff that happens. in general, they're surprising movements by people intersecting you in various ways. And that's important, right? I think you need to have very quick reactions to deal with this. And it's maybe also important not to do these things when you don't have to also, because also braking all over the place is the converse problem, right? So this is another interesting case. Watch behind the bus. So, thank you. And you can join us to build these kinds of large models, and there is some of our research and our safety research on these sites for those that are interested.
Thank you very much, Drago. And we have time for just one quick question.
Yes. Hi.
Thank you for the great talk. What are the biggest roadblocks that are stopping this technology from becoming widely available to everyone?
So I'm not sure there is one big factor. I think we're just doing a thoughtful rollout as the hardware, the software, and the safety story keeps progressing. We keep scaling, right? I think it's not obvious one should just flood entire cities from zero to some huge numbers immediately, right? I think we're doing, as we roll out and improve all the aspects of our economics, of our sensor vehicle platform, and the machine learning, that allows you to keep scaling and scaling thoughtfully without causing more issues. I think that's mostly that. Generally, I would say that the more we go out in the world and the more we see the variety of issues, and I think I tried to give you some idea, I think the more there's appetite to advance machine learning, because it's a tool that can address scalably a diverse set of issues, right? In that area, whenever it works, it's more powerful than human engineers, which address the issues one at a time. So I think it's been a great tool for us. We've tried to stay at the forefront of machine learning for our domain, and we have strong motivation to keep doing it.